Hey, welcome back to Crafting a Crawler, and we're back looking at our game dev algorithms again. Oh, there we go. A little bit more visible now. But yeah, so last week we worked a bit on some maze algorithms. So we set up the room. We set up a generator for grid-based rooms generation, and then we also configured our first maze generator, which was Prim's algorithm, which is still here as is. And then we applied that to some of our other generators. So using the binary space partitioning, for instance, we were able to then apply Prim's algorithm to that to get, as well as Delaney coordination, triangulation to connect. So we used Delaney triangulation to connect all of the rooms, and then Prim's algorithm to decide which of the edges that we would actually keep. And that helped us to generate far more far more interestingly connected rooms. So we run this like a couple of times, we get we get a more sensible flow to the layout. We still need to at some point look at our tunneling algorithms, see if we can do a better job than say this, where it sort of connects off of the to the side. So potentially we can look at more S-shaped connections, where whereas at the moment we're going across and down, we could go like across, down, across, or potentially look at other ways of connecting them. But yeah, maybe some more intelligent decisions around whether or not we go up or we go up first or across first. So this one, for instance, is starting in the center here, coming down and then across to join the centers of the rooms, whereas if it had gone up from here, it would have provided us a much cleaner tunnel. So that's stuff we can look at in the future. And yeah, so that same maze-based logic gives us some nice layouts in the sort of more internal shapes as well. But where it really shone was when we started looking at grid-based layouts. So let's close that down. Yeah, so when we looked at the grid-based layout, hi Aaron, welcome in. We then get an actual maze. I mean, as mazes go, this looks pretty maze-like. The trouble is, it's not a particularly good maze. It's not a particularly good maze. 1 second. Yeah, I mean, a lack of minotaurs is definitely something we can address at a later date, but the problem is the algorithm. So Prim's algorithm is a algorithm that calculates the minimal spanning tree of a graph. A graph being wanky technical talk for a bunch of distinct things that are connected together. and then the things that connect them are the connections are, we then call edges. So our maps are actually a graph. We have the rooms, and the rooms have edges that connect them. So what Prim's algorithm does is it looks for the smallest. It tries to work out the smallest, least costly connection between all of the nodes on the graph. So it'll try and connect all of the rooms so that they are as well connected as possible. What this like the distance between any two nodes is tries to keep them at a minimum, without introducing any loops and things like that. So what we end up with is it is very heavily biased towards very short dead ends. So we see a lot of the forks go off, and they're very short forks, and that each of those has even more smaller forks. So there's no like little windy dead ends. Just a lot of short and not particularly useful ones. So I think we'll try and look at some more algorithms today, and hopefully we'll find some that will we'll hopefully look at some that will generate a I'm trying to remember the terminology now. They'll generate some other spanning trees that are slightly less biased towards the shortness. If we have a look at our browser, so as I said, this is all based on graph theory. A lot of image generation is based on graph theory. So here we have all of the rooms being connected, and then it's sort of picking the route between those nodes and opening them up to each other. So this, as I mentioned, we did prims. There we go. Sorry, a uniform. The word I was looking for was a uniform spanning tree, which means that the distance between things is sort of less biased. The only trouble with these algorithms, though, is they tend to work similar to our drunkard walk, and they share some of the problems that those have. So remember our diffusion limited aggregation, for instance, is a similar concept. And the trouble we have is at the beginning, when the spot it's trying to find is very small, we get a very slow generation. If the existing coverage of what we're looking for is small, so I think Chrome is being very stupid lately. Okay, so we have Wilson's algorithm seem to be the two that will get us Wilson's algorithm and Aldos-Broda seem to be the two that will get us the result we're looking for. So Wilson's algorithm will randomly pick a point and then drunkard walk until it finds the SWAT. So this is similar to our DLA algorithm, and the Aldous-Broder algorithm seems to be a similar seems to be similar to the drunkard's walk. So we could look at some of those. I think, yeah, although the least efficient, Aldous-Broder sounds like it would be the easiest for us to implement. The trouble I see with both of these is that Wilson's will be very good, will be very slow at the start, but quick at the end. So if we look at the sort of GIF of it generating a map, here it takes quite a while to find its roots at the beginning, then picks up after, fills in quite quick, whereas the Aldous-Broder sounds as if it will be the opposite, so it will be quite slow towards the end, but quick at the beginning. Okay, so let's have a crack at implementing some of these though. So let's add markdown. Let's get rid of the browser window. So we'll go for the Aldous-Broder. Let's grab how do we define this? Okay, pass, and then we want to return the generator. Then we want to render this out. And maze Aldous-Broder, drop that into our okay, so with this we want to pick a random cell. We can probably reuse some of the setup from our previous from our prims algorithm. Okay, so we're going to get the list of points. We're going to get the number of points that we have and the number of edges that we have. So then we want to pick a point at random. So we'll go between, random and the width. And we'll have a list of the cells of the various nodes that we visited. So now we want to walk randomly. So we want to pick. We've got our current cell. So while we haven't visited every cell, we're going to set the current one to true. We also want to process this edges into neighbors. So we'll create a array of arrays, sorry, a list of lists, and then so for each of the edges, we'll create a list of sets actually. Then so that should give us a and then we're going to want to pick a, so if we look at the pseudocode for the algorithm, so we pick a cell at random and mark it as visited. So we've done that. While there are unvisited cells, pick a random neighbor. Choice even. So we're going to pick a random neighbor from the neighbors array. If the neighbor hasn't been visited, we also want to keep track of our walls. So if the neighbor hasn't been visited, we will go, we'll append the current we'll append the neighbor and we will add the neighbor, we'll set the neighbor as visited, and then we set the neighbor as the current cell, and then when we return then we should okay, so we've got, so the algorithm was pick, let's just indent this slightly so that it matches what was on the page. So yeah, so we pick a random cell as the current cell and mark it as visited. So our current one, we pick one of the rooms at random. And then we mark that as, actually we can, let's rearrange this a bit to make it more accurate. Okay, so we pick a random cell, mark it as visited, done. So while there are unvisited cells, so while not everything in our visited list is true, which is while there is matches that, pick a random neighbor. So we look at our table of neighbors from up here. We need a list to inspect that, so maybe maybe we are better off with lists here. I'm just thinking, otherwise we're going to be converting sets into lists over and over again. So what we can do is go if it would help if I could spell today. And if A is not in neighbors B, for B, there you go. So that'll give us the same result. We'll get neighbors will be just one entry for each neighbor, but we're going to do the work up front rather than continuously converting it to a list later. So yeah, okay. So we pick a random neighbor. So we look at our neighbors and we pick one of those. We choose a random thing from our neighbors array. If it's not visited, then we add the link between our current cell and the neighbor to our list of edges. And then we mark it as visited, and then we continue onwards. Then if we run this, okay, that is not what we expected. We should reuse the drawing code as well, I think. Um, let's, instead of copying this, let's actually no. I was thinking, could we abstract this, which is I'll tidy this up later. For now, we'll copy pasta it, and then we'll come back and make it clean and nice later. So we want to create a new image. Then we want to draw between each of the points, and then for v in. Then for each of the results, we want to do the same. Draw it a bit darker. Well, I'll consider it's light and dark. A bit lighter. Okay, so this is actively turning into a mess. Let's try with a much smaller. Oh. Let's try with a much smaller grid. So what has this actually done? So it's connecting randomly. That is not correct. So first let's have a look at our neighbors. Okay, that is definitely not correct. If we look at the edges, so these look correct. So why is it creating a weird combination here? For B in, yeah, for A and B in edges. So this is just creating, this has added everything into the first. Oh no. Okay. It's connecting everything to everything. How many edges does this actually generate? 360. So seems sensible. Let's scale it back to 5 so we can actually see. Actually, let's go down to 3 so we can actually see in far more detail what's going on. Yeah, so each thing is ended up connecting to everything else. Oh, I know what's going on here. Okay. It's because I was an idiot. So I created one array, inner array, and created a bunch of copies of it. Thanks for joining, Aaron. So when I just times the array, it had this. The inner array was just replicated into each item of the array. So every time I added to it, it was one reference to the same list. So it just kept extending it. Here we go. Whereas now if we run it, we get a far more sensible set of options. And we get a more interesting layout. Okay, so now if we scale this back up, let's look at a 10 by 10 maze. Then if we go to 50 by 50. Okay, it's not the most efficient algorithm, but it's not taking too long. And it's still a 1/10 of a second to generate the maze. So how does this measure up against our previous contender? I mean, we're still getting a lot of short passages. but it's not bad. I think we've got less of them though. It's just, so we still get a bunch, but not quite as many as we did. Or am I imagining that? I wish I could. Oh, actually, hang on. Split. Here we go. So I can put them side by side. Try and get them. So let's get my ugly mug out of the way. So I think we have got an improvement here, right? From the looks of it, the Aldersbroda algorithm has given us a much. We've still got a lot of short dead ends, but I think that's just the nature of backfilling the spaces. But I think the actual paths, we have a lot less of them, I think, than we do with the prims. Yeah, this is not bad. Let's okay, let's have a look as well and see what that gives us in some of our other layouts. So if we generate this one twice, and instead of prims, we'll go for Maze Aldersbroda. I think we will fix the seed as well, so we get a similar result from each. Oh, I pressed it again, expecting another result, but we fixed the seed, so therefore we get a consistent result. Picking another random seed entirely at random, and by that I mean not random at all. It picks a very different. It picks a different sort of path. What if we increase the number of rooms? If we generate 20 rooms instead. Oh, I think we need to turn some of the other knobs down a little bit as well. Okay, I mean, both of these are interesting. I'm not sure which is that. I'm not sure if either is objectively better though. Yeah. I mean, I think we do get slightly more interesting layouts with the Aldo Sproda, but the from the structure point of view, I think we're getting more interesting ones out of here. But the end results, though, once it's all rendered, I'm not entirely sure there's that much. It makes that much of an impact. Okay, that's interesting. Let's set this back to what it was. Okay, let's have a look at some other algorithms. So we've got the Aldersbroda. The other one was Wilson's. Which doesn't seem to have a good definition that we can easily convert into code. Okay, let G again be the graph, and let V and W be two vertices in G. Construct a random path from V to W inductively using the following procedure. Assume we already have defined let F be the function from G to R satisfied. Okay, this one I might have to do some more reading on, as there is no. We don't have any helpful definition available just quickly on Wikipedia or anything. So I'll have to read something a bit deeper. We could also look at a recursive implementation. So doing a depth first search. Okay, this one shouldn't be too hard to implement. So let's add Markdown and some code. This is a okay, so okay, so if we define our maze generator, and then we want to have a there it is. We have our randomized depth first search. So with this, we've got our edges, and then we want to pick a cell at random again. So start is going to be a random room. We're going to want to calculate the neighbors again. We'll store what has been visited. Now I think we want another function. So this, we want the we then want the neighbors, which is a list of integers. And then we want the visited, which is a list of integers. That is not what we're doing. Okay, so I'm going to return none. Hang on. We can while the stack is there, no, hang on. Let's do this as recursion first, and then we'll look at converting it into a stack. Okay, so we have current room. We have the visited rooms. Our neighbors. Yes, and we have the results. Okay. So we're going to go, we mark the current as true in our visitor table because we are currently there. Okay, and then for neighbor in, oh, we need our random function. Take a copy of the options. We are going to shuffle them so they're in a random order. And then for each of our randomized neighbors, if it's been visited, then we will continue, else we'll append it to the list of results, and then we will recurse down. So then we just go results is an empty list, and then we go search. And then we return results. So what we're doing here is we're calling this function with our first random choice of room. And we've marked, we have a visited list that says all of the rooms aren't visited. We have our mapping of the neighbors. And then we have an empty list of results. And then we're just passing our random number generator along with us. So with that, we mark the cell as having been visited. We effectively get a randomized list of the neighbors, and then for each we loop over those neighbors in a random order, and if they've been visited, then we carry on. We don't do anything, and we go to the next neighbor. But if they haven't been visited, we add a link between our current node and the neighbor, and then we continue on from that new neighbor. We run this whole logic all over again. So then the neighbor is now current, We mark it as visited, pick amongst its neighbours at random, loop over for any that isn't visited, so that exclude the one we just came from, and any other neighbours we may have visited. And then if we find any, we append, and if not, then we end. And then we keep going, nesting our function calls deeper and deeper and deeper until we find one where all of the neighbours have been visited, and then we return back, and then we'll go, which effectively means we go back to the previous cell the previous room we're in, and then we continue looking at its neighbours until all of its neighbours are done, and then we'll go back and continue back until we get everything explored. Okay, so if we try this now. Oh, see that? That is a nice looking maze. This I like. We have nice long corridors here of connections. We do have a few short dead ends, but they're by far they are by far like less frequent than sorry. They are by far less frequent than in the other algorithms that we've looked at. So if we get some more up here, yeah, if we put this next to I'm not sure what I was expecting, but for some reason this is the sort of maze I was expecting from Orders Broda. I was expecting like a uniform spanning tree to potentially have less dead ends than the minimum spanning tree, but that's But yeah, it's very different, and we can see in comparison like the prims is even more dead endy. So I guess this is probably more of a bias is more towards a maximal, towards a like a maximum spanning tree. Yeah, I think with an alternative at the other end, I think I can actually now see. I was struggling to see the difference between the prims and the Orders Broda before, but I think with a more extreme example, the other end, I can actually see how this is in the middle now. But yeah, this is what I'm talking what we're talking about. This is nice. So what happens then if we were to take this and apply it to our binary space partitioning. So if we were then to use the DFS maze generator on Ooh. Okay, we're not drawing the. Okay, I definitely need to abstract this before our next. I need to abstract and tidy this bit up, but I can do that. I'll do that after. I'll do that off camera. I don't think we necessarily need it in here. But yeah, so if we draw split. Okay, this is choosing very different routes to what we've had so far. I think I like it though. Oh, these are actually generating different rooms. Sorry, different patterns. So let's put the standard seed equals. And let's standardize the seed so we can get a proper comparison between the two. Oh. Here we go. This way we'll get a different but consistent one each time. Yeah, this is giving us a much more windy path. I mean, this one doesn't actually have any forks whatsoever, so if we tweaked the values on here to prevent the bleed over from one room to another, this would be a very nice path. But even like this, with the rooms combining a bit, it's not terrible. Let's reduce the post-processing from the D. Yeah, I think the roots we're getting now. Yeah, some of these are much nicer. Much nicer. We have more of a progression in these because the route tends to have one long path. I mean, it's getting slightly. Some of the funky corridor generation is not helping us here, but we're getting something more biased towards a long sort of progression rather than a big bunch of different paths that we could take. So like the distance between here and here is going to be a lot longer. or here and here, than what we have on the minimal spanning tree, in which things are a lot more closely connected. But both, I think both have value though, I think. So I think the Prim's algorithm and maybe the older Broder will give us nice sort of exploration maps, whereas the depth first search based maze will give us a nice sort of progression, more of a gauntlet style level, where effectively we're going from room to room. Okay, let's let's reset that once again. Yeah, so I think with this new algorithm what we've got is something that worked really well for a gauntlet, for any kind of gauntlet style level. So imagine a progression of room after room, clear each room before moving onward style level. Whereas the minimal spanning tree, and the uniform spanning tree, I think give us more exploration focused ones. So something where there's we can spawn a bunch of secrets and points of interest down different routes. Another option we can also look at is potentially we take the minimum spanning tree or the DFS tree and so on, and then we add in some of the removed edges back. So like we could add maybe 1% of the removed edges back to the map, and that'll give us some loops and things in there as well, which could be interesting when we have a high number of rooms. Okay, so we've got two algorithms now. Do we want to try and convert this into a stack based? The trouble with recursion is that most languages have a limit on the depth you can go with a recursion. Which means that we can only nest inside each other too much. So if we have a very complex room or a very complex layout with a bunch of different rooms, we could start hitting problems in some languages. And we want to try and keep this as generic as possible. Like we're going to have to port anything we build here back to that we choose to keep and make it into our final set of generators is going to have to go back into Lua. Okay, so if we were going to do this as a stack, we would have a stack here and we would add the start to it. we would skip our call to the recurse. While the stack is set, we're going to take the current value, if okay, so if all of the neighbors are visited, then we're going to continue. Else we want to push ourselves back onto the stack because we've got stuff to visit. Sorry, we want to mark. Ooh. Yeah, sorry, we want to mark the current cells visited. Then, if all of the neighbors have been visited, actually no, here we go, yeah. So I'm just thinking, otherwise we're going to be setting this to true up to 4 times. So we only want to say it once. So I'm going to push this back. We're going to take the random neighbors again. No, options equals I for I in neighbors. If it hasn't been visited, yeah, then we shuffle those. Actually, so neighbor is equal to RNG dot choice of those random of the unvisited neighbors. So we're going to create a list of all the neighbors that are not visited, and we're going to pick one of those at random. That'll be our neighbor. We are going to append a edge between the current and the neighbor, mark the neighbor as visited, and add the neighbor to the stack. So now if we run this, we get an error. Oops. That is me spending far too much time in different languages lately. Okay. Yeah. So, okay, we've got near enough, pretty much the same results out now. It'll be slightly different, but close enough that what we could also do is No. I was thinking we could potentially remove the neighbours as we go, but because it's two ways. Yeah, I think this is... Okay, so that gets rid of our recursion. Yeah, I am very happy with the results of this one. I think this is... This is also known as the okay. And there is another algorithm we could look at called Kruskal's, but that also generates a minimum spanning tree, so it shouldn't actually be too different to Prim's. I'm just having a look at the other algorithms we have. Fractal tessellation, I don't think we want to look at. All right, I think this is good. So let's have. I think we're kind of done for maze algorithms now. So, yeah, I think it's going to be a short one today. I was kind of expecting this to take a bit longer, but it's flown by, and we've actually got far nicer results than I had expected. So I might actually call it for the day. Cut our losses while we're ahead. But I am very happy with the results here. This is this is a very nice looking maze as far as I'm concerned. I think we've done quite well, and I was kind of expecting this to be a lot more. See, I was expecting this to take longer to run as well. I was expecting it to actually run quite so quick. I think it might actually be the quickest. Yeah, no, they're all. Yeah, they're all about the same, I think. Prim's is faster, but yeah, I think we got some good results out of this. And then I think next time we will potentially look at some biome mapping. So this is where we've already looked at one of the, this is where this is, at the moment we've been mostly looking at how we carve up the space. So we've been looking at effectively carving out caves from the walls, whereas the biomapping will instead give us a way of saying, okay, so this region here is, say, we'll have a swamp here, and then that will bleed into some grassland, and next to that maybe some desert, but and like plains next to that, but still not having the desert and effectively not having a desert and a swamp sat around next to each other, so they're actually sort of separated out. As that sort of generation wouldn't really make much sense in the real world. We could do that with something we've already looked at, which is the open simplex noise. We can use that to generate some of our random sort of biome. Where is it? Oh yeah, it's up here. Basic generators. Simplex noise. So we can use this. At the moment we're rounding this, but what it gives us is a nice gradient of between 1 and 0 that flows into each other. So we can use this and some other types of noise to generate some criteria that would then add on to that would then combine together with other factors to generate our biomes. So we could do that, or we might actually look at Voronoi cells. That could also be the something, as Voronoi cells also will not only allow us to generate interesting layouts. A Voronoi cell is the inverse of a Delaney triangulation. So if we look at something like this, by picking random points around, a Delaney Voronoi cells would pick the points equidistant from other cells and draw the lines between those. So we could use that to generate some interesting sort of cave shapes, but also would be useful in our biome generation. So yeah, okay. So I think next week we'll start with Voronoi cells, and then after we've looked at those, maybe we'll look at some biome mapping. And that will be next week's work. And once we've got the biomapping in, then we can start to port some of this back into our existing Lua code, which would then allow us to start generating some maps, which probably means I should start working on some more pixel art, so that we've got more tiles for different types of ground that we'd need for different biomes. So yeah, that will be next week. If you're as big a fan of the mazes that we've generated design, give the video a like, drop a subscription and on the channel, and hopefully I will see you next week for some more game development. Bye.